Good morning, everyone. It's Mr. Havenhill, and I've got the final two tests that we are going to be utilizing to determine the convergence of an infinite series, and they're known as the ratio and the root tests. In my opinion, they're actually among the easiest to use, and they're fairly powerful too, because they can determine not just convergence, but absolute convergence in a relatively quick, quick couple steps. So let's go ahead and let's get started with the ratio test. Now, the ratio test is going to sound just as its name implies. We're going to be dealing with some kind of ratio. And let's go ahead and take a look at it. If we have a series with non-zero terms, then one of the following three results is going to be true. Number one, we would say that the series converges absolutely if the limit of the absolute value of the n plus first term over the nth term is less than 1. We would say that the series diverges if we take that same ratio, the limit as n approaches infinity of the n plus first term over n plus, or the nth term. If it's greater than 1, or if it's equal to infinity, then we're going to say that the series diverges. And then if that ratio equals 1, we will say that that is the results are inconclusive and we have to do a little bit more digging. And so this test is pretty straightforward. And as long as we can get either step 1 or part 1 or part 2 here, we can determine convergence, divergence very, very quickly. When we get into step 3, well, then we hit a dead end and we're going to have to do some more work, and I want to show you an example of that in a few moments here. So let's take a look at the first example. I'll give you a chance to write it down. Go ahead and hit pause. Okay, so what we want to do is determine the behavior of the limit as n approaches infinity of a sub n plus 1 over a sub n. And we want to compare that to 1. If it's less than 1, absolutely convergent. Greater than 1, divergent. Equals 1, well, then we go back to the drawing board. So let's go ahead and let's take a look at what is the n plus first term going to look like here. Well, we're going to take the limit as n approaches infinity. And I'm just going to, everywhere I see an n, I'm going to replace it with an n plus 1. So that's going to be n plus 1 squared times 2 to the n plus 1 plus 1 over 3 to the n plus 1. And then we're going to divide that whole thing by a sub n. N squared, 2 to the n plus 1 over 3 to the n. Okay, so let's do a little bit of algebra here. I'm going to rewrite this. I'm going to multiply by the reciprocal, and I've got n plus 1 squared, 2 to the n plus 2 with your permission. 1 plus 1 is dos. And we have 3 to the n plus 1 down here. And then I'm going to multiply by the reciprocal of this quotient, 3 to the n over n squared times 2 to the n plus 1. Okay, now we just simply are going to go through this and do our best to try to simplify. And so it'll be nice to have our exponent rules somewhat handy. I'm going to rewrite this as 3 to the n times 3. And I'm going to rewrite this guy here as 2 to the n plus 1 times 2. And check this out. We have 3 to the n's are going to cancel out. Whoosh, whoosh. We're going to have 2 to the n plus 1. Whoosh, whoosh. Cancel out there. And that big intimidating thing is going to look like this. That whole expression is going to reduce to 2/3 times n plus 1 squared over n squared. Now this right here we unfortunately can't reduce just yet, but what we can do, or in terms of simplifying, it's not like we can just cancel the n's, but what we can do is imagine that the numerator would be an n squared plus 2n plus 1 over an n squared. And when we're dealing with this ratio, as we're trying to analyze what happens when n goes to infinity, all we really care about is the n squared over the n squared. These terms right here, they're not going to make a contribution to that limit, and as a result, this limit right here, this limit is actually just 1. And here's what we end up with. We have 2/3 times 1, and since that's less than 1, what does the ratios test tell us that about our series? That's right. A sub n is absolutely convergent. Okay, let's take a look at this particular example. We've got the series as we go from 1 to infinity of n to the n over n factorial. Wow, that thing just looks amazing. That looks really, really fun. So let's go ahead and let's take a look at what happens when we employ the ratio test. Let's take the limit as n approaches infinity of a sub n plus 1 over a sub n. We've got the limit as n approaches infinity, and I believe that's going to be n plus 1 to the n plus 1 power divided by n plus 1 factorial divided by n to the n divided by n factorial. With your permission, I'd like to go ahead and just write it like this. What I've done is I just multiplied by the reciprocal. Okay, so we're going to need a little bit of help with simplifying this. If I recall correctly, n plus 1 factorial would be equivalent to n plus 1 times n factorial. Why is that? Well, I know it's been a while since you probably have studied probability of any kind, unless you're taking stats with Mr. Martin. But n factorial is the same thing as n times n minus 1 times n minus 2 times blah 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 until we get to 3 times 2 times 1. Well, what would n plus 1 factorial be? Well, I claim that it's going to be n plus 1 times n plus 1 minus 1, but what's that? Yeah, that's just n. And so essentially what we have is the remainder of that whole expression, and so n plus 1 factorial is simply going to be n plus 1 times n factorial. And when we look at this, the n factorials cancel out, and we have something that looks, when we clean this up a little bit, we have n plus 1 to the n plus 1 power over n plus 1 times 1 over n to the n. Well, that's kind of cool. I believe that the n plus 1 is going to cancel with one of these up here. Now, again, your algebra skills have to be absolutely on point to see this. We're not canceling n plus 1 with the n plus 1. What we've got here is n plus 1 to the n plus 1 power is the same thing as n plus 1 to the nth times n plus 1 to the 1. And when you combine those, it's just like this. 3 squared times 3 to the 4th is 3 to the 2 plus 4, which is 3 to the 6th. That's Algebra 101 right there. All right, so here's what we've got. We have n plus 1 to the n over n to the n. Wow, okay, so what do we do with that limit? Well, what's nice here is they both to the nth power. So I can do a little bit more algebra and make that n plus 1 over n to the nth. That's going to give me the limit as n approaches infinity of, I'm going to make that n over n plus 1 over n to the nth. And some of you can already smell what I'm cooking here. That should give me 1 plus 1 over n to the nth. Now turn to the person next to you and ask, do you recognize that limit? I hope so. That right there is our good old friend e. Well, e is definitely larger than 1, and therefore, by the ratio test, our series diverges. Okay, we've got one more example for the ratio test, and I do want to warn you, this is going to be a more involved problem. This is going to take up some space, so I don't want anyone to get lost, but I think this is such a valuable problem, especially because of all that it helps to review and whatnot. So I just want to give you fair warning, it is going to be long, but let's go ahead and let's jump straight into it. So the first thing we're going to try to do is determine whether this series converges or diverges, and we're going to consider the ratio test, even though we see that it is an alternating series. But because we have a new toy, let's see if we can play with our new toy. And so we're going to let a sub n equal the square root of n over n plus 1. And what we want to know is the following question. What is the limit? What is the limit as n approaches infinity of that ratio, the ratio of the n plus first term to a sub n? So let's go ahead and let's see what we've got here. We've got the limit as n approaches infinity of the square root of n plus 1. On the bottom, that's just going to be n plus 2. By now, I'm hoping you'll just give me permission to multiply by the reciprocal, and that would give me an n plus 1 over a square root of n. Okay, so let's see what happens here. We've got the limit as n approaches infinity of, I'm going to rearrange this since this is just the product of two fractions. I can rearrange my terms a little bit, and I'm going to have n plus 1 over the square root of n, the square root of n plus 1 over the square root of n, times n plus 1 over n plus 2. Okay, so then from here, I'm going to do one last little step. I'm going to look right here, and I'm going to make that just one gigantic square root problem. Okay, so the limit of a product is equal to the product of the limits. And so the first limit I want to consider is the limit of the square root of n plus 1 over n as n approaches infinity. That's just going to be the square root of 1. And the limit of this ratio here, n plus 1 over n plus 2, as n approaches infinity, well, that too is just 1. Okay, so what we have is that the ratio test gives us 1. And that means that the ratio test is inconclusive. Well, since this is an alternating series test, since this is an alternating series, perhaps we can employ the alternating series test. And so this is going to get a little bit more involved here. Now, some of you might be thinking to yourself, well, that was dumb, Mr. Havenhill. Why don't we just use it to begin with and save us all that time? Well, the truth is the ratio test, sometimes it will work. And we want to be able to utilize all the tools we have at our disposal. And I want to give you I also want to kind of model what would happen to some of you where you might be working on something and you don't just get straight to the final answer. You might have to spin your wheels a little bit. You might hit a brick wall or a dead end. And so let's go ahead and let's see what happens here. Let's try and see if we can employ the alternating series test. So What we need to show are two things. What are those two things? Lean over to the person next to you and identify them. All right, you guys got one of them. You have to show that it's a decreasing series. That is, the term on the left is larger than the term on the right. Okay, and what's the second one? That's right. You need to show that the nth term approaches 0. Okay, so let's go ahead and let's compare. We've got the square root of n over n plus 1. How does that compare to the square root of n plus 1 over n plus 2? How do we determine which one's biggest? Well, if we have a calculator handy, then we can start plugging in n values, and that's one way that we can try to determine which is larger. But let's go ahead and let's practice using some a more rigorous approach, and that would be using some first semester calculus from AB Calc. And what we're going to do is model this series by a function. And what we're going to do is analyze the first derivative. And remember that if the first derivative is negative, it means your function is decreasing. If the first derivative is positive, then it means it's increasing. So let's go ahead and, if we were to take the derivative of this thing, we would have the derivative of the bottom times the derivative, the bottom times the derivative of the top minus, we use the quotient rule, low d high minus high d low, minus the top times the derivative of the bottom all over the bottom squared. And after you simplify that, you're going to end up with negative x plus 1 over 2 root x times x plus 1 squared. Now I've already taken the time to simplify this right here. Hopefully what you're seeing though is that for all values of x that are in the x values that we're even interested in trying, and which x values would we be interested in trying? All the n values from 1 to infinity. So we're looking at all positive x values. So for all x greater than 1, this upside down a doesn't mean anarchy. That's the symbol that mathematicians use to mean for all. So for all x greater than 1, what we have here is that f prime of x is negative. If you plugged in 2, that would be negative 2 plus 1, and the numerator, no matter what, is going to be negative. If you plugged in 3, you would have negative 3 plus 1, negative 4. Doesn't matter. For all values of x greater than 1, then we end up with something that is going to be less than 0 in the numerator and positive in the denominator, so therefore this thing is decreasing. Okay, so we have satisfied the first part of the alternating series test, the conditions for the alternating series test. Now let's go ahead and see if we can demonstrate the second piece right here, that the limit as n approaches infinity, the nth term approaches 0. So let's take the limit as n approaches infinity of the square root of x over, sorry, I'm still in function mode. Let me go back into series mode here. Well, when you plug in infinity, essentially, or if you try to evaluate this limit, we're going to get infinity over infinity. What do you do here when we have an infinity over infinity? That's right. Call 911. That is, get ready to go to the hospital. That's right, we're going to use L'Hopital's rule. Use L'Hopital's rule. So that's going to give us the limit as n approaches infinity of 1 over 2 root x divided by 1. The derivative of the top is 1 over 2 root x, and the derivative of the bottom is just 1. And when we take the limit as n approaches infinity of that, so that's going to be 1 over infinity, that equals 0. Okay, so here's what we've got. By the alternating series test, our series converges. Does it converge conditionally or absolutely? Well, that's what we have to now investigate. So, how do we analyze that particular series? Okay, so what's kind of intriguing here is we have a number of tests that are available to us, and what I'm going to try to utilize is something that we haven't probably thought about in a few days here, just because of the nature of the new material that's been coming our way. What I want to use is the limit comparison test. So, just to remind you, the limit comparison test, what we want to do is take a sub n, and in this case that's the square root of n over n plus 1, and we want to try to figure out some kind of b value, another series that's close to this, but is some kind of multiple of a sub n. So we're going to delete the terms that are not needed here, and I claim that a great candidate would just be the square root of n over n. And if I were to rewrite this as n to the 1/2 over n to the 1, then that's going to be reduced to 1 over n to the 1/2, or 1 over the square root of n. Okay, so we want to now consider what happens if we take the limit as n approaches infinity of a sub n over b sub n. And so what we have is the square root of n over n plus 1 divided by 1 over the square root of n. Let's simplify that a little bit. Well, if we're going to multiply by the reciprocal, then that's just going to be the square root of n over 1. And well, what's the product of the square root of n over the square root of n? Or sorry, the square root of n times the square root of n. Yeah, that's just n. And what's the ratio of that particular limit as n approaches infinity? Exactly. That equals 1. Okay, so we need to ask ourselves, what do we do here? What does this mean if we had that when our limit is equal to 1? Well, the limit comparison test said that if you have a sub n is equal to c times b sub n, that if one of these converges, the other has to converge. And if one of these diverges, the other has to diverge. Well, what do we know about this series? 1 over the square root of n? That's right, it's a p series with p less than 1. It must diverge. Whoa, what's happening to my pen here? And so, since this particular series diverges, it means that our original a sub n must also diverge. By the limit comparison test, the absolute value of n diverges. Okay, so let's put all the pieces together. The alternating series test gave us that a sub n converged. The limit comparison test said that the absolute value diverged, so therefore our series is conditionally convergent. All right, folks, we are now ready to take on the last of our tests, and this is what's known as the root test. And it's actually the 3 parts to it are very, very similar to the ratio test, and in that the series is going to converge absolutely if after we apply our mojo we're going to get something less than 1. Our series will be divergent if after our process generate something that's greater than 1 or equals to infinity. And this particular test is also inconclusive if, when after we do what we do, the result equals 1. So what exactly are we doing with the root test? The root test is pretty straightforward. What we're literally going to do is take the limit as n approaches infinity of the nth root of the absolute value of our series. And it's really actually a pretty straightforward algebraic application. And this works really well. This test works very well when you're dealing with powers to the n factorials, things of that nature. And so here we go. Let's go ahead and let's try an example. Or actually, I've got a couple examples here for you. So, are the following series going to be divergent, absolutely convergent, or conditionally convergent? Let's go ahead and let's take a look at the first problem right here. What we're wanting to do is simply take the limit as n approaches infinity of the nth root of a sub n. All right, well, what is that going to look like? We're going to take the limit as n approaches infinity of the nth root of e to the 2n all over n to the n. Well, this looks intimidating at first unless you were to rewrite this as e to the 2n over n to the n, and this thing to the 1 over nth power. The nth root is equivalent to the 1 over nth power. And now when we try to simplify that, all of a sudden, this doesn't seem as intimidating anymore. This is e to the 2n over n divided by n to the nth over n. And what we're left with is the limit as n approaches infinity of e squared over n. Well, principle of dominance here. E squared that's just a constant squared, so that's just a constant value, and the bottom is going to get it's going to approach infinity. So the bottom's bigger than the top. What we then say is that this limit equals 0. Therefore, by the root test, our series converges absolutely. Bam! We don't even have to worry about conditional convergence. We've got absolute convergence, just like that. Okay, give you a chance to jot that down. And let's come and take a look at this guy. Let's classify the convergence or divergence of this particular series. The series as n approaches, or as n goes from 1 to infinity, as of this alternating series, negative 1 to the n times n to the n over 5 to the n plus 1. So let's take the limit as n approaches infinity of the nth root of a sub n. Well, what's our a sub n? All we care about is the value of this series here. We're not concerned, just like with the alternating series test, we're not concerned with this negative 1 term right here. And so what is that going to look like? That's going to be the limit as n approaches infinity of the nth root of n to the n over 5 to the n plus 1. All right, so I think that's going to be n to the n over 5 to the n plus 1 to the 1 over n power. From here, the algebra is actually pretty straightforward. It's not hard at all. That's going to be n to the n over n. And then what I'm going to do here is rewrite that as 5 to the n times 5. And that's going to be to the 1 over nth power. I'm doing that on purpose so that you can see in here. The numerator is just going to be n, and in the denominator that's going to be 5 to the 1 times 5 to the 1 over nth power. And well, what's going to happen here as we let n approach infinity? What we end up with essentially is something that's going to approach infinity. Therefore, by the root test, our series is divergent. Just like that. I hope you will agree with me that these two tests, the ratio test and the root test, once you've had a chance to really utilize these, they're very powerful and they're very quick in terms of the results that they yield, as long as we can show that either our ratio or the root will be less than 1, we have absolute convergence immediately. If our ratio or our root is greater than 1, we have divergence immediately. When we have to start doing some additional work is when, after applying both techniques, we end up with a value that equals 1. And so we have completed all of the tests that we have been developing, and what I'm going to ask you to do now is the following. This is going to feel very tedious at first, but you're just going to, I hope that you'll trust that this is a worthwhile exercise. As a summary exercise, what I'm going to ask you to do, whoa, come back here, full screen please. What I'm going to ask you to do is go to the table on page 646 of Larson. It's on my site if you want to pull it up. And I'm going to ask you to take time to copy the chart and, if necessary, add your own comments. This is going to be in addition to the homework that I'm going to ask you to complete. Your homework for tonight includes this chart and work from the Larson text. And see my site for the exact assignment itself. Here's what I mean by this. So here's what you're actually going to see in the text. You've got the test, the series, then you're going to have a column for conditions of convergence. There will be a column for conditions of divergence, and then some ancillary comments, some comments where you might want to put some very useful insights that you have when applying that particular test, or limitations of that test, or side effects of the test. For instance, if we were to look at the nth term test, we take our series, a sub n as n goes from 1 to infinity. All this test can do is tell us if something diverges. There are no conditions for convergence for this particular test. However, if our nth term doesn't equal 0, bam, we know that this is a divergent series. And as a comment, this test can't be used to show convergence. All right, we have a geometric series. What does a geometric series look like? Well, we've got something that's some kind of term a, who knows what it could be, it doesn't really matter, times a common ratio. Well, when will that series converge? When the absolute value of our ratio is less than 1. When does this series diverge? When the absolute value of r is greater than or equal to 1. And as a great summary here, we can actually compute the sum of that infinite series. In fact, this was the very first series that we were able to compute the sum of. And the sum is equal to the first term divided by 1 minus the ratio. And we're going to continue on in that manner to go through all the different tests that are on that page. And I really ask that you don't just try to copy it down robotically, but use it as an opportunity to connect the dots and to remind yourself of what we've been working on for the last several weeks. There's a lot of material here, and I know we tend to only remember that which is freshest in our mind, the most recent material that we've covered. And this hopefully will give us a chance to kind of dig up a bunch of material that we haven't thought about in a few weeks. So after you've done that, or as a part of your assignment, what I'm going to ask you to do before you get started on that is the following. And I'm going to ask you to work on these 7 questions where you're going to simply determine the convergence or divergence of each series. And of course, by now you should be used to trying to determine if it does converge, is that absolute or is that conditional? And I just want to let you know that the solutions to these, to all 7 of these, are in example 5 on page 645. So what you're going to do is try all 7 of these with your crew And some hints are on example 5. And then after that, I'm going to ask you guys to work on the table and then work on the assignment. So thank you guys so much. Please go ahead and pause here so that you can work on all of these. And that's all I have for you guys. I hope you have an amazing day.